Hello, Tanya Laird here, and welcome to part 1 of lecture 15 of ENGR 231 Engineering Statics. In this portion of the lecture, I would just like to go through some of the basic theory of applying the formulas of centroids or calculating centroids for composite or compound areas. So, centroids of composite or compound areas. Of composite or compound areas. So, first of all, let us review what we've looked at so far. Previously, we have looked at how to find the area of a centroid that would be described by a single continuous curve. Or a simple shape, I might also say. Centroids of simple shapes. Of simple shapes defined by a single curve, or a single continuous region. By a single continuous region. So, for example, we have looked at how to calculate the centroid of one example that we have worked through was finding the centroid of a triangle, or at least a right triangle. And we've also looked at how to find the centroids of, say, a simple region that was defined by, say, a parabolic curve on below and a linear curve above. That's, again, a relatively simple region. The shape is relatively complex, but the region itself is relatively simple because this can be calculated by a single zone of integration. So when I'm talking about a composite or a compound shape, I am talking about a shape that requires more than one curve to define, or I would have to define or perhaps I could define the top and bottom curves by a series of piecewise functions. So, for example, instead of looking at a simple right triangle, imagine I want to define for example, the centroid of a region like this. Let me draw this a little bit bigger. What if I wanted to find the centroid of a region like this? So let's say it had, well, not like that, not a simple right triangle or a center at the origin or position at the origin, but maybe something like this. Maybe a triangle that is not a right triangle at all. And again, the nice thing about the right triangles, well, I want to draw something that's clearly a right triangle. That's clearly not a right triangle. So let me get my drawings right. Here we go. We'll draw something that's clearly an obtuse triangle. Something kind of like this. So this is clearly not a right triangle. A really big triangle on this slide here. And again, for a right triangle, it's relatively simple to find the centroid of that. It's just 1/3 from the bases. But what about something like this? Here, the simple right triangle formula is not going to apply. Now, we could break this up into a series of right triangles, or 2 right triangles. There's one right triangle here and another right triangle here, but neither one of these is, or not even neither one of these, each one of them is themselves a right triangle, but the combined shape is certainly not a right triangle that we can apply a simple single formula to. Or other examples. Other examples would be things that don't even have a single, that aren't even a single simple shape like a triangle. So we could get some really elaborate regions. For example, imagine we had a rectangle combined with a triangle. This would be a trapezoid, essentially. If I wanted to find the centroid of this, I couldn't just look up a single formula that would describe, oh, well, actually, there might be some for this particular case, but it would involve, the dimensions of this width here and this width here, so each of them would be important. But it wouldn't be, I guess we probably could if we wanted to derive a single formula for this, but it wouldn't be something as simple as just a basic formula involving a width and a height or something like that. It'd be a lot more complex. But of course, or I can also say that, or we should probably consider that these shapes can get arbitrarily complex, even to the point where we might deal with things. Consider something really odd like this. Oh, what if I had a shape like this? Maybe there's one rectangle here, and then another rectangle here, and then I have a triangle here, and just for fun, I could have, oh, I don't know, a semicircle here. If I had this really complex shape, how would I find the centroid of this? I could do this via integration. Because we remember previously, if I say, for example, I wanted to find the x bar of this, we said that x bar was equal to qy over a. Well, the way I'd have to do this, well, a would just be the same area, but if I wanted to use integration approach for this, I would basically have to break qy into 4 zones of integration. If this was zone 1, 2, 3, and 4, I would have to say my qy is a qy1 plus a qy2 plus a qy3 plus a qi4. I would basically have to calculate the first moment of area with respect to the y-axis for each one of these regions and then sum them together. But at that point, that gets rather cumbersome, and there probably is a better way. Also, what if you have something that has a hole in it? What if there is negative area present? So for example, what if you have a region like this? Let's say you have a trapezoidal region. And what if there is, say, a circular hole here? So you have a solid area here with a hole in it. How do you find the centroid of something with a hole in it? Or, in something more familiar to mechanical or civil engineers, something like a wide flange shape. Something we've discussed before. This is basically a rectangle with 2 rectangular holes in it. How do you find the centroid of this? Well, actually this one's fairly trivial. If it's a doubly symmetric, the centroid would still be right in the middle. But what if it wasn't symmetric? What if you had something kind of like this? What about something like this? Something that is clearly not symmetric, at least about the x-axis. Here, it might be symmetric about the y-axis, but this is clearly not symmetric about the x-axis. So you could think of this in terms of a big rectangle with various holes in it, or you could think of this as 3 rectangles put together. But how do you find the centroid of one of these shapes? Something that I refer to as a compound or a composite shape. And the way you find these fundamentally is not by integration. For composite shapes, or maybe I could actually define a composite shape. A composite or compound shape is one that cannot be solved or analyzed using a single integral. And there are other definitions we could look at as well, but in this context, I could define a composite or compound shape as one that cannot be solved or analyzed using a single integral. Using a single integral. Instead, we need to combine the results of multiple integrations together. Of multiple integrations together. And fundamentally, we are going to do this using tabular methods. To do this, we will use a tabular method. And where does this come from? Well, if you remember back to the first part of the previous lecture, we mentioned how we could do a weighted average of point particles. to find the center of mass of a point particle. So remember, if we have multiple masses, say along the x-axis here, say you have an M1, an M2 at a certain distance x2. Actually, maybe I don't want to put any. Maybe I don't want to put any particular one of these at the origin. So maybe I just have an M1, an M2, and an M3. And we could say these have the coordinates, x-axis coordinates. We have the x and the y of x1, x2, and x3, the individual x coordinates. Well, remember, I introduced this to explain, I introduced this as a introduction to how we use integral methods when calculating centroids of areas. But the overall x bar here, in terms of center of mass, would be x1 times m1 plus x2 times m2 plus x3 times m3 divided by the summation of the mass, which is m1 plus m2 plus m3. And this is just a center of mass calculation from basic physics. The center of mass method for point particles. At least along a single axis. But you could do the same thing by averaging the y coordinates if you were dealing with a two-dimensional system. And effectively, we're going to do something incredibly similar, basically the same thing, when looking at areas, or area centroids. When averaging areas, or in finding the centroids of compound shapes, we effectively do the same thing but with areas. The same thing but areas. But with areas. So for example, maybe I'll illustrate this in a generic form, and I think I'll have a part 2 of this lecture where we look at a few basic examples. So let us say we have a xy plane where we have two rigid bodies. One rigid body and another rigid body. So this is going to be rigid body 1 and then rigid body 2. And this thing has a center of mass here. And this thing has a center of mass here. And so I could label the coordinates of those as, maybe the center of mass of this one, or sorry, I should say centroid rather than center of mass, because this is not really talking about a mass so much as centroids of area. So I would say these have centroids of x bar 1, comma y bar 1, and x bar 2, comma y bar 2. So how would I handle this? Well, I would create a table as follows. So I would have basically I usually start this with a column for n, basically just a piece label. And this is especially important for very complex shapes. But for this particular example here, we would have or this general example here, we'd have just pieces n, 1, and 2. Then I would have a piece, maybe like AI, and this would represent the area of each of these pieces, an area 1 and an area 2. Then I would have an x bar I, the x coordinate of the centroid of that given piece, and the y bar I, the y coordinate of the centroid for each of these pieces. And this would just be whatever that coordinate is, x bar 1, and whatever that coordinate is, y bar 1. And then for this one, this would be x bar 2, whatever that x coordinate happens to be, and then the y bar 2, whatever that coordinate happens to be. Then, just like we did here, where we multiply the coordinates times the masses, I did the same thing but area. So I have an AI x bar I and an AI y bar I. And so this would be A1 x bar 1, the product of those two, and then A2 x bar 2, and then A1 y bar 1 and A2 y bar 2. Literally just multiplying the coordinate of the centroid of each piece times the area of that given piece. Then I would sum this column up to get the A total. The summation, basically just a summation of area. Then I would sum these up. Well, actually, I could just call that A total for now. Or I guess I could just call that A, the total area. The summation of AI x bar I is basically going to be your QY, the first moment of area, with respect to the x-axis. And so then the summation of this here, the summation of the AI y bar I, is basically the QX, the first summation of area with respect to the x-axis. And then the overall combined x bar is just going to be this column here, the summation of all the individual AI x bar i's and then divided by the area, or just the QY divided by the area. So I could just say this is, if I want to do summation, I could say, if I wanted to indicate this by summation, I could say this is the summation of AI x bar I divided by the summation of the individual AI's. And then y bar, the overall combined y bar, the y bar of the entire shape, is equal to the summation of AI y bar I divided by the summation of AI. And that really is the basic formula, or those really are the basic formulas and methods for calculating centroids of composite or compound shapes. And really, that's really it. Or really, I probably shouldn't use the word really twice in the same sentence, but really, that's it. It's really nothing more complex than that. In part 2 of this lecture, we will work through an example or two of this, but essentially that's it. It's just applying this basic tabular method of multiplying distances times areas, and then performing summations of the columns and then divisions as necessary. The only other thing I might mention in this theory video is how to handle holes. And actually, holes in shapes are very easy to handle. For holes in shapes, for example, back to this problem here, we had this hole here. Holes are treated as just another object or another piece. Treated as any other piece or part of a body. Or part of a body you simply give them negative area. Simply assign them negative area. Negative area and calculate as regular. As you regularly would. So if I put a negative, if one of these particular pieces has a negative area, this number here, the area of that particular piece will be negative, and then the AI x bar I, assuming the x coordinate is positive, for example, would have a negative value, and that would then end up subtracting from my overall first moment of area with respect to the y-axis. And we will see some examples of that in part 2 of this lecture. All right, I think that'll do it for part 1 of this lecture. For part 1 of lecture 15, please let me know if you have any questions. This was just meant to be a brief video covering some of the theory of, or covering the theory and basic method of calculating the centroids of composite or compound shapes. Again, please let me know if you have any questions. If not, I'll see you soon for part 2 of lecture 15. And as always, thank you.